Yeah, again, welcome to the third week. You're able to see the screen, right? Just please, yeah, thank you. So, this is about week three, structural analysis one. And in this, we will be discussing about the analysis of the statically determinate truss structures, mostly the truss members, using method of virtual work. So, let us directly go into some. I just want to give some concepts behind the virtual work. Usually what it is defined is, let us say this is a beam or any kind of a structure, and it is having some different types of boundary conditions or different types of supports. And when this beam is having external loads, these are called external loads, right? Like the UDL and the point loads, which usually we have. So let us say these are the external loads that those are acting on this beam. And for example, if you want to find displacement in this direction at some other point, okay, this direction, what we usually do is we'll assume the same beam, and then we'll apply a virtual load. Okay, so the virtual load means it's not actually present on the beam, but just for our calculations and just for finding out the necessary information or the necessary details. So we usually apply virtual load, and this virtual load should be at the place of interest. So this is our point of interest. At this point, we want displacement in this direction. So along the same direction at the same point of interest, we'll apply unit load. P is equal to 1. So this can be 1 kilonewtons, so on and so forth. So if we want to find rotation, then we'll apply unit rotation. Theta equal to, bending moment is equal to, or the moment equal to 1 kilonewton meter. So in this case, what we'll do, we'll apply to the same beam without any real force. So in this, you can see there is no real loads here. I have only applied a virtual load of P equal to 1, and because of that, I'll have internal loads developed. I have internal forces developed. So let us say this is internal forces U, and because of this real load, so this is the actual scenario. Because of this, I have internal deformations developed. Let us say this initially the length is L, and it has elongated up to dn. So if this is the case, what we'll do is 1 in 1 multiplied by delta is equal to summation of internal forces due to virtual loads into deformations due to the external loads. So this is what we'll do. I'll just tell you what happens in the case of truss also. Okay, let us say this is a truss member. This is a truss member. The truss member. I have an external load acting like this, P. Let us say this is load P equal to, let us say this is some 10 kilonewtons. So if I want to find what is the vertical displacement here at this point, let us say what is the vertical T equal to how much, then what I'll do is I'll first solve for P equal to 10. I'll just solve what are the forces in this truss. I'll have some forces in this truss. Let us say something like this, and then I'll take the same truss, and then I will apply a vertical deformation or the vertical displacement. So I will apply a vertical displacement of vertical force of, let us say, P virtual as 1 kilonewton, and then I will solve for the forces. So in this, let us say my forces are P1, P2, and P3 in this truss, and in this case, what I'll get is I'll get, let us say, V1, V2, V3, let us say. So if this is the case, if you want to find out this deflection, what you just simply do is delta 1 times delta. So this is unit load, and in this direction we have delta is equal to summation of what I said, u into dl, right? So this u are nothing but these v's, v1, v2, and v3 are called the small u's because these are internal forces developed due to external or the virtual load. So these are the u's. And what about dl's? Dl's are deformations or deflections. Let us say deformations due to external loads in the members. So this is a truss member, right? So truss member can have axial forces. Let us say this is axial force, so it is actually in compression. This P1 is in compression. I'm talking about this part. So if it is P1, let us say the length is L, and you know area of cross section and Young's modulus E. So what is the deformation? dl of 1 is equal to dl by AE. Okay, so this is for this member. The dl is P1 L by AE. So you'll sum it. So you have three members. So you'll have three different. You'll have three different uh, combinations of u times 3. So likewise, how we can write is v1 into, so I'll say this is dl1, this is dl2, and this is dl3. So what I'll write is u v1 into dl1 plus v2 into dl2 plus v3 into dl3. If I just simply do this, I am going to get what is delta. So this is the theory behind the virtual work. Again, I'll just repeat. If you want to find out the displacement at the at some point because of the external loads, what we'll do is we'll apply a unit load, a unit virtual load. Why do we apply unit virtual load? It's simple. So it is one top times delta, right? So we are indirectly finding out what is delta there. It's one multiplied by delta. So you apply a unit unit load of P is equal to 1, and then you find out what are the internal forces because of this virtual load. Those will be U1, and also find out what are the internal displacements or deformations due to these external loads. Those will be dl1. So you just multiply internal forces in the member and its corresponding internal displacements due to the external loads, and you just summate it and you'll find out what is the delta. So this is the concept of the virtual work method. Okay, so let us directly go to the problems. Today we'll solve as many problems as possible. So the first one is you can see this. It's a triangular kind of it's a truss member. So in the question, determine the horizontal displacement of point C. So what is the horizontal displacement at point C? For each member, the area of cross section is 400 mm square. Young's modulus is 200 GPa. So now the question is the horizontal displacement at point C. So if you want to find out the horizontal displacement at point C, first initially you need to solve what is happening in this number because of the given external load. So this 40 kilonewton is external load. Okay, the support reactions which are generated are the support reactions. So we can't you cannot say it as an external load because those are the reactions which are developed due to those external loads. So initially, first solve for the internal forces due to these external. So the internal forces are the ones which you usually solve for. Let us first solve internal forces due to external load. This is the first one. Let us solve for it. So we'll just solve like this. So we already have this triangular number and pin and the roller support here, and this is 40 kilonewtons. This is 40 kilonewtons. So what we'll do is we'll just take uh, what can we, yeah, this is A, this is B, and this is C. So this distance is about 8 meters, and this height is about 3 meters. So actually, I just want to tell you something. So in all the problems which we are dealing today, right, that will be in the ratio of something like this. If this is 4, if this is 3, this will be 5. Okay, this is 5 square, that is equal to 4 square plus 3 square. So in some problems we also have something like this. If this is 1.5 and this is 2, then this will be 2.5. Okay, so in all the problems which we are discussing today, right, so this will be how the dimensions are. So if you see if, let us say if this is theta, then cos theta will be 4 divided by 5, sin theta will be 3 divided by 5. So this you just make a note of it so that it will be easy for us to start working. Okay. Yeah. So internal forces due to external load this much. So what are the support reactions? Let us solve it quickly. Now by now I think you are very much you can solve this. So V10 that is equal to 40 times 3. So this is 15. VB is 15 kilonewtons. So this is 15 kilonewtons. Then what about this? This should be minus 15 kilonewtons because there is no external force to balance it. So the support reaction itself should balance. So it's something like that. When you are pushing this in this direction, this is exerting some compression in this direction, and usually you will have a tensile force coming in this direction. And then when you have this as 40, then there should be 40 in this direction to counteract, right? So this is 40, this is 15 downwards, this is 15 upwards. So so far so good. So what we'll do, let us take this point A. So this is point A, this is FAC, and let us say this is FAB. Okay, at this joint we have 15 kilonewtons downwards, and we have 40 kilonewtons towards the left. So what we can do, let us say this is something. So let us take this as theta. So FAC times cos theta minus 15 equal to 0, so I'm just writing it as 15. So FAC, so cos theta is again, how much is this length? This is the height direction, so this is 3, and hypotenuse is 5. So because you can see here, this is 4, the height is 3, and this length will be 5. So FAC cos theta is 3 divided by 5, and that is 15. So FAC is 25 kilonewtons. As we got it as positive, that means it is in tension. So this is already in tension, 25 kilonewtons. And what about FAB? So FAB, I'm solving here, FAB plus FAC times, let us take this as theta now, or I'll take this as alpha. FAC cos alpha minus 40 equal to 0. Okay, so FAB plus FAC is 25, cos alpha is like 4 by 5 this time because this is alpha. Cos theta is again adjacent divided by hypotenuse. This is 4 and this is 5. Minus 40, that is equal to 6. Okay, so how do we solve this? Yeah, 5 times and this is 5. 5 was 20. So FAB is equal to 20 kilonewtons. So you got this as 20 kilonewtons and again in tension. So likewise, you can find out this. This is like, yeah, there is this, yeah. So let us take again the point B. You have FBC here. You have FBA, and this is FBC, and this is upwards 15. So what? How do we find? So I'll take this as theta. FBC times what is theta? So theta is this. This is 3 divided by 5. 3 divided by 5 plus 15 equal to 0. So FBC is minus 15 times 5 divided by 3. This is minus 25 kilonewtons. That means it is in compression. So initially we have assumed tension, so we got it as compression minus negative, so it is in compression. So this is the summary. You can see FAC in tension 25 kilonewtons, FAB in tension 20 kilonewtons, and FBC is in compression 25 kilonewtons. Right. So what I'll do is I'll just summarize the results. I'll summarize the results here. Is this visible or shall I make it full screen? This is fine, right? You're able to see this or full screen mode is better? So this is A, B, C. A, B, this is C. So we have something like this. This is intention 25. So 25, I'm not writing the units, so just kilometers, take it as kilometers. This is 20 and this is 25. Okay, so now let us just now this is done. Due to external forces we have obtained the internal forces. So these are the internal forces. Due to external forces of 40 kilonewtons, the internal forces in the members are these 25, 25 and 20. So you have to also mind uh, the direction or the sign, whether it is tensile or compressive compression. So next, what is the next one? So next one is the virtual. So the we have the truss, the same truss without any external forces, but apply the virtual load in the direction of the displacement which we actually want. So in this, it was asked that determine the horizontal displacement of joint C, horizontal displacement of joint C in the truss. So horizontal displacement of joint C. So in that direction, you apply the force, unit force one. So it should be 1 kilonewton. That's what it means. So you have again this is 8 and this is 3. Okay. This is 3 meters and this is 8 meters. Let us solve quickly for this thing. So we have 1, 8 and 3. So let us say this is A, C and B. So VB, vertical reaction at B, vertical reaction at A, we have horizontal reaction at B. So horizontal, you can just simply say this is 1 kilonewton. So at A you should have a leftward 1 kilonewton. Should I, because to balance this. And what about VB? VB times 8. So this is rotating in this direction about this point. What about this? This is rotating in this direction. So it should balance. So this is 1 times 3. So VB is 3 by 8. So if VB is 3 by 8 kilonewtons, what about VA? VA should be downwards 3 by 8 because there is no external vertical force acting except for this 1 kilometer. So this is 3 by 8 upwards and this is 3 by 8 downwards. Okay. Now what happens to the internal forces? Similarly, you can work out the internal forces. So the internal forces you can see. I'll just work out for AC and remaining rest of the things. I think I already have some solution. So you that I'll just write down here. So let us say this is A, point A. This is AC, FAC, and this is FAB, FAB. So the again you have support reaction which is downwards 3 by 8, and you have a support reaction which is one towards the left. So let us take this as vertical and let us take this as theta. So if this is theta, that means adjacent side is this. So this is 3 meters divided by 5 meters. Just a second. Someone just joined. Okay. So FAC times cos theta should be equal to 3 by 8. FAC times what is cos theta here? Cos theta is 3 by 5 is 3 by 8. So FAC is 5 by 8. Okay. So FAC is 5 by 8. Similarly, in the same similar lines, you can find out FBC and FAB. So I have already worked it out, and I'll also tell you a small trick in this also at the end of this once I have done this. So this will be okay. Anyways, I'll solve for this one also. Only this one and the other one I'll just mention you the answer. So FAC, let us say this is alpha. This is alpha. FAC cos alpha. Okay. Plus FAB. Okay. Uh, minus 1 equal to 0. So FAC we already know. What is it? 5 by 8 times cos alpha. In this if this is alpha, this is 4 and this is 5. So this is 4 by 5 plus FAB minus 1 equal to 0. So FAB is, what is this? So FAB is 1 minus 1 by 2, that is half. Yeah. So FAB is half. This is 1 by 2 attention, and this is worked out to be in compression, and that is 5 minutes. I'll just tell you a trick in this. So you just see the question like this. So if you see the question, what is the question? It was asked the horizontal displacement of joint C. The horizontal displacement of joint C is asked here. So the external load is already given as 40, okay, 40 kilonewtons. So if the external load is already given and the external load is also acting around the direction of the point of interest or the displacement which we need to find, right? So in the same direction, it is the question is asked for horizontal displacement at C. In this direction, what is the horizontal displacement? So we have external load also acting at only at there. There is no at any other points. There is no external forces acting, right? So what happens is that you find for external loads of 40 kilonewtons, what are the internal forces? So we already found it, and the answers are 25 in this member, and 25 in this member, and 25 and 20 in this member. So when you are applying instead of 40, now you are applying only 1 kilonewton. So what happens? It gets divided by 40, right? So in this what happens? 25 divided by 40, that is 5 by 8. In this what happens? 25 divided by 40, that is 5 by 8. In this 20 divided by 40, that is half. So you can directly say if there is no external force acting. So if there is external force acting, then your answers may vary. So this is overall summary. So these are the forces due to the real loads, and these are the internal forces due to the virtual load. So now how to find the displacement? So delta. So I'll just write out AB. We have AB, and we have AC, AB, AC, and BC. So let us write in this term. So length. Let us write length. Length first, and we have U. U. What is U? U are the internal forces due to the virtual load of 1 kilometer. And what is DL? So DL is nothing but P PL by AE. Okay. So what is P in this again? So because of this, I'll just write down first what is P. So we have U, we have capital P. Let us write this. So in what is the length of AB? AB is 8 meters. What about AC? AC is again 5 meters. What about BC? BC is 5 meters. What about U? So in AB, what is U? AB, what is U? Half in tension. So I'll write positive tension. I'll take it as positive. What about AC? AC compression 5 by 8. So minus 5 by 8. What about BC? BC is in compression 5 by 8. So again, this is 5 by 8. Now, what is P? P again, P are the forces in the beam due to the real loads or the external loads. So let us first write for AB. In AB, tensile 20. So tensile 20 plus 20. In AC, in AC, tensile 25. What about BC? Compression at 25, minus 25. Now this we have done. How to find delta? Delta is actually summation of U times DL. So what is DL and what is U? So in this we have three members. So U is varying from 1 to 3. So we have UI DLI1 plus U2 DL2 plus Q3 DL3. Now what is DL? DL is nothing but, let us say, DLI. PI Li divided by Ai Ei. In this we have A is constant for all the members. So this is constant. So let us say this A and D. So we have L varying and also Pi varying. So for the first member, that is AB, now how do you find? So let us just multiply all these things here itself. So what we'll do is we'll have PUL. Okay. So what about this 8 times half times 20? 8 times half times 20 is 80. This is 80. What about the other one? 5 times minus 5 divided by 8 times 25. Minus 78 point. Sorry, AC is the tensile, so this is tensile. 78.125. And what about this? So minus times minus plus again, so 5 times the same thing. So 78.125. So when you do the summation of these, so this plus this plus this. So what we'll get is uh, summation is equal to 236.25 divided by AE. We have AE. So delta is equal to 236.25. So now you just be careful when you're converting the units. So in this, the load is taken as kilonewtons. So I want to convert it into newtons, 10 to the power 3, and meters length is taken as meters. So I'll convert into millimeters. So that is 10 to the power 3. And what about the bottom? So in the bottom we have A. A is how much is A? A is 400 mm square and E is 200 gigapascals. So this is 400 mm square, it is fine. And 200 gigapascals is 10 to the power 3 megapascals and megapascals. So 1 gigapascal is 10 to the power 3 megapascals. So if 1 megapascal is nothing but Newton per mm square. So that is what I've taken. So you may ask me why I have taken. I have P as 1 kilonewton. I mean in kilonewtons, and U is also kilonewtons, right? So why did I take 10 to the power 6 here? So the answer is in this. If you remember the previous equation, is 1 dot delta is equal to U into dl. This one is nothing but 1 kilonewton. So that's why I didn't consider changing the sign. I didn't consider 10 to the power 3 here. So this is nothing but you'll get it as 2.9, 2.95. Just, just a minute. So this is fine. This is 2.95. So the vertical displacement at joint C, the vertical displacement, sorry, the horizontal displacement at joint C is 2.95 mm. So this is the answer. Any questions? Yeah. So okay, this 236.25 by AE, right? So this is the answer. This is what we get after doing the summation. So what happens here is in this all these things are in kilonewtons. This is in kilonewtons. This is in meters, and this is also in kilonewtons. Okay. So when you multiply this, I want all the things should be in newtons and mm. So that is the reason why I have multiplied 10 to the power 3. Okay, one 10 to the power 3 is because of kilonewtons converting into newtons, and another 10 to the power 3 is meters converted into mm. Yeah, and I also have this u which is kilonewtons, but this is being cancelled because due to this 1 kilonewton. I'm multiplying a unit load, right? One times unit load is du into dl. So this the kilonewton over here, and because of u, you have a kilonewton over here. This gets cancelled. That's why I didn't multiply another 10 to the power 3 here. Yeah. So this is again everything is in mm. So usually it's better we calculate all the deflections in mm because we'll never see deflections in meters. So that's why I wanted to calculate everything in terms of millimeters. Okay. Shall I go to the next question? Thank you. So let us. My PPT got stuck. I just close it and I'll just reopen it. Yes, I will open the new slide. Yeah, sorry, actually I don't know. There's some issue, so I just started a new slide. Anyways, let us solve it. So fine. Now the question is again similar type of the question. We have determine the vertical displacement of joint B in the truss shown in the figure below. AE is constant. So in this, they did not provide us any numerical for A and E, area of cross section and the Young's modulus. So in this, what shall we do? We shall. So what is the procedure? So we'll first solve the real truss system. Real truss system in the sense we have some external loads. It is 150 kilonewtons. We'll solve for this. What do we mean by solving? So we'll just find out what are the internal forces. Internal forces are nothing but the compression and tensile forces in the truss member, each truss member, and we'll find out what are the deformations for each truss member. That is the first part. Second part is we'll apply unit load in the direction of the displacement which we are interested to find. So again, we'll just start the question again. First part is real analysis. Real analysis. So in this we have a beam something like this. Oh, sorry, truss beam something like this. Something like this. We have a roller support here, and this is A, B, and C. So this is 150 kilometer. This is 6 meters, and this is 8 meters. Yeah, so this is 150 kilonewtons, so there is no vertical force here to actually resist this 150 kilonewtons, so you should always have a vertical force here, so this should be 150. And if this is let us take moment about C0, so let us take this as horizontal A, so HA times 6. This is rotating this point in this direction, so it is rotating this hinge here in this rotation. And what about this? This is rotating this in this direction, so HA times 6 should be 150 times 2. So this is how much? HA times 6 is this 150, so this should be 5. HA is 200 kilometers. So this is 200. This is 200 kilonewtons. So now this should obviously be 200 in this direction because there is no any rightward forces acting. So if this should be 200 and there should be something which is balancing, so this is again 200. So again, this is very simple, like we solved yesterday, right? Like I mean the last class. So the last session. So we have seen this point. This is perpendicular here. So if this is perpendicular, if this is taking 200, that means this should take 200 in tensile direction. And if this is taking 150 in this direction, and this should be 150 in tension direction, then the only thing which we need to solve it is for this. Okay, for this. So let us take joint A. Let's take joint A. So joint A is this, and we have FAB in this direction, FAB in this direction, and we have horizontal force or the horizontal reaction 200 kilonewtons coming in this direction, and this is tensile forces of 150. Okay, so how do you solve this? So this is theta. Let's say this is theta. So FAB cos theta. FAB cos theta plus 200 should be 0. This is theta. What is this cos theta? So this is 8 divided by okay. So this is 8 and this is 6. So again, this is something like in this fashion. This is 8. This is 6. This is nothing but this is 4. This is 3. This is 5. So this is 10. That's it, right? So this is something like 3, 4, 5 again. Um, so F A B cos theta. Now this is cos theta. So cos theta is 8 by 10 or 4 by 4. So 4 by 5, that is minus 200. This is 5. So F A B is minus 250. So minus means it is going into compression. So it is going into compression of minus. So this is minus 250. Yeah, so real analysis is done. So what are the internal forces? PC is having tensile forces of 200 kilonewtons. AC is having tensile forces of 150 kilonewtons, and AB is having compressive forces of 250 kilonewtons. So let us solve for the virtual truss. So what happens for the virtual truss? Now let us use the concept which I was telling you earlier. So now the question is, now the question is to find the vertical displacement of this joint. So if you see by inspection, you can see that there is a real force or the external force of 150 kilonewtons acting vertically here, and if we that has to be replaced with the unit load of 1 kilonewton acting vertically at joint B, right? So that means all the forces in the member, it is again all the forces in the member will be divided by 150. That's what it means, right? So I want this to be 1 1 kilonewton. This is nothing but 150, which is the earlier asked, divided by 150. So similarly, everything will be proportionately decreased, right? So what are our earlier answers? So this 200, the force in CB is 200. That will be 200 by 150. That would be 200 by 150. Then what about the forces in AC? 150. So 150 by 150. 150 by 150. And the force, sorry. Forces in AB. AB is minus 250. So that is again minus 250. So 250. This is quite simple, right? So again, let us make a nice neat table of our AB. What are the members? We have AB, one member, AC as another member, and we have BC. So we have three members. Three members. So we need length of each member. We need internal forces of each member due to the unit vertical load or the unit virtual load, and we need internal forces due to the real loads or the external loads, and we need P, U, and L. So what is the length of AB? AB is already given 8 meters. So AB is 8. What is U? U in AB. U in AB is 200 by 150. 200 I'm just writing it as 200 by 150. 200 by 150. What about P? P is 200 tension, so that's why it's positive. What about AC? AC length of AC is 6 meters. What about U? 150 by 150. You can see here this is in tension, so positive, positive, positive. What about P? So P you can see here. P is 150 in tension. So 150 in tension. What about BC? This is BC. Length of BC is 10. This is 8. This is 6. So this is 10. This will be 10. So what about U? U is minus 250 by 150. What about P? P is again minus 250. Yeah, minus 250. So now you have three members. So actually it should be one times delta is summation of u times dl. So that is u1 dl1 plus u2 dl2 plus u3 dl3. So dl is nothing but each member deformation in each member. So that is nothing but pi. Dli is pi dli by ay ei. So in this ae is said to be constant and the value is ae itself. Lengths are changing and p is changing, so that's why we have actually we try to tabulate the values of l, u and p which are changing. So you find out what is this and this and this, and then you do summation. So that will be, if you do, let me do for them. 200 times 200 times 8 divided by 150. Yeah, that is 2133. So in this it is 150 square times 6 divided by 150. 100. So this is 900. What about this? 250 square divided by 150 times 100. So this is 66 plus 600. Total put together is 2200. Okay, this is 2200. But what we need is delta. Delta is nothing but we only found out uh, this thing u times pl. U times pl is the one which we have found out, but as a is constant, we need to that has to be divided by a. So the answer is 7200 divided by a. So the vertical reaction, so the vertical displacement at joint B is 7200 by a. Okay, so this is the answer. And if in case we were asked to find out what is the horizontal displacement at joint B, so we'll have this thing similar. The real analysis will be the same. There is no change because the real analysis is the internal displacements due to the real loads. So the real loads are nothing but the external loads which are acting on the member. But the only thing which changes is instead of giving vertical force something here, we need to give a horizontal unit load of 1 kN, and then find out each term of this. To find each term, so instead of multiplying with this term earlier terms, you will have a new terms, new ui, u1, u2, u3 terms. So you just multiply each thing and you find out what is the horizontal displacement. Any doubts in this? I hope this is clear. I'll move to the next question. This is the next question. Let me go to the next one. Yeah. Again, this is similar. Not much complicated. This is similar. So let us do the same thing. Solve for the member forces in the truss shown in the figure below. That will do. However, what are the forces in the members BC, AD, what is it? AD and AE? That is fine. Where A is the area of cross section and E is the Young's modulus. Okay, that is fine. And there's one more thing which I missed here. Yeah, what is the displacement at joint B? So it is asking for the displacement in joint B. So yeah, it is asking for the displacement at joint B, this joint. So again, let us start with the real analysis. So real truss analysis, that is what I mean. So let us simply draw. Just so we have this truss member. We have the truss member here, and this is a roller support, and this is a hinge support. This is D, A, B, and C. So 15 kilonewtons, and this is also 15 kilonewtons. So let us find. Yeah, Uh, let us find the support reactions first. Okay. So yeah, we can find the vertical reaction of this support E directly. So at support E, so usually sorry, it is not vertical reaction. So we can find the horizontal reaction at supporting. What is the horizontal reaction at supporting? You don't have any external horizontal forces in this, so the horizontal reaction at this support is 0. Right. Now, what is the other one? We have a vertical reaction at A and vertical reaction at E. So what I'll do is I will take vertical. Let us take moment about A as 0%. So that means this vertical reaction at E. So V E times. So you can see this. So this is the lever arm. So it's trying to rotate in this direction. So which direction? This anti-clockwise direction. And these two loads are trying to rotate this point in clockwise directions. So V E times how much is this? 8 is equal to 15 times 4 plus 15 times 8. And this is VE is worked out to be 22.5. 22.5. So this is 22.5. So if this is 22.5, how much this should be? 22.5 plus x is equal to 15 plus 15, that is 30. So this should be 7.5. It is balanced. No, everything is balanced. The system is imbalanced. So everything is in balanced condition. Now let us find the internal forces directly. So like I said, you just check this by inspection. By now I think you need to answer this. By inspection, we can say that these both members are uh, perpendicular, right? Both members are in perpendicular. They are actually uh, they are orthogonal, right? So if these members are orthogonal, that means this should be equal to this. So this is 0 directly, right? What about the other one? This should be equal to 22.5. So this is 22.5 intention. So this is direct. Now if this is 0, now check this point. At this point, so you have 15 kilonewtons tensile acting downwards. So this member and this member are again orthogonal. So this has to carry 15 kilonewtons. Okay. Now what about this? What about this member? This member we can only check by this point. So let us take this point A. Let us take this joint A. And you have AD in this direction, FAD, AD, and you have what is the other one? FAB. You have FAB in this direction, and the support reaction, which is in vertical directions, 7.5. So now let us take this as theta. Okay. So again, this is again something like this: 4, 3, this is 4, and this is 3. That means this is 5. So what we are looking at, this is theta. This is theta means this is 3. This is 5. So FAD times cos theta plus 7.5 is 0. That means FAD times, what is cos theta here? 3 by 5 divided by 5. That is minus 7.5. This is 2.5. That is again AD is minus 12.5 kilonewtons. So let us mark it up. So FAD is minus 12.5. That is 12.5 in compression. Now what about FAB? FAB is FAD times this theta, cos theta. That is, this is alpha. So what is this cos alpha? This is 4 divided by 5, and that means 12.5 times 4 by 5. This is 2.5. This should be 10. So there is nothing here, so this should be 10 again. Okay. Now what is remaining? Yeah, this yeah, only this one is remaining. Now how to find this? So we already know this is 22.5, and this is 15. So there is an extra force of unbalanced force of 7.5 in this direction. So that should be balanced by this. Okay. So let us say this is FCD. FCD. So FCD times, and let us say this is theta. If this is theta, how much is this theta? This is 3 by 5 again. 3 by 5 is equal to unbalanced is 7.5. This is 2.5 and FCD is again 7. So this is FCD is 2.5 and this is but it is another page. So what do we have? We have yeah, we have at this point. Let us take this as C, joint C. So we have CE force as 22.5 in tension. CE as 22.5 in tension. This is the first point. And what about the other one? We have FCE as 10 again. FCE as 10 in this direction. Okay, all right. And yeah, we need to find FCD. FCD has to be found out. And what about the support? Do you have any supports here? Yeah, there is one. Okay, there is no support, but there is yeah 15 to so we have an external load of 15 kilonewtons here. So how do we find? We can either take FCD, uh, FCD, what is it? FCD plus this FCD. Let's take this as alpha. FCD cos alpha plus 10 equal to 0. FCD cos alpha. How much is this alpha? This is 4 and this is 5 and this is so that is 4 by 5 is minus 10. Okay, what is this? FCD is minus 50 by 4, which is minus 12.5. That is this thing is in compression. This thing is in compression. This thing is in compression. 12.5. So we are done with real analysis. Now for the virtual load or for the unit load, where do we need to apply the load? The vertical displacement at joint D is what is required to find out, right? So we can apply the vertical or the unit load at this displacement in this direction. So this is the unit load. So let us do the so now let us do the virtual have a virtual test something like this. This is the plus. Sorry, it's not. Oh, sorry, it is not virtual truss. It is the real truss, the actual truss, but we are applying a virtual load. Okay. So this is 1 kilonewton because at this point we need to find out vertical displacement. So this is 1 kilonewton. And again, I don't want to repeat the same procedure. I'll just give you the answer. Maybe you can cross verify and you can cross check. So let us say what are A, B, C. This is B, C, A, B, C, D, and E. So what happens is that because of this, you just find out. I have already worked out. So this is zero point 0.5. This is zero point 0.5. Okay. So there is no external force. There is no horizontal force. This should be zero. There is no horizontal force. And each member will have this is compression 0.833. I think it's better if yeah, I will solve one for one joint. I think that's a better thing to do. So I'll solve for this joint A. Joint A, you have a tensile force FAD. Let us say FAD, and this is FAB, and this is zero point 0.5. So how do we arrange? So let us say this is theta F A D cos theta. Cos theta. How much is that? FAD cos theta. plus 0.5 is 0. FAD times cos theta. What is cos theta? That is, this is 3. So 3 divided by 5 is minus zero point 0.5. So FAD is minus 2.5 divided by 3, that is 0.833. This is 0.833. Similarly, at each joint you can do this force equilibrium, force summation fx, sigma fx and fy as 0, and then you can find out. So I'm just giving you the answers. So this is 0.667, and this will be again 0.667 tension. And what about DC? DC is in, it is again tension 0.833, and this is in tension 0.5, and this is 0. Why it is 0? So you can see here, this is 0. There is no force from in this direction, so there will not be there will be no force in this direction also. So what about point B, joint B? So at joint B, this joint you don't have any vertical force. So in this member, the force will be 0 because it doesn't have any force to actually carry it, right? So there is no force in that vertical member. So to let us, I'll just summarize the real and the virtual forces. So okay, I'll just copy paste. So we have this member. Okay, in this member, what are the real forces? First I'll write down the real forces. I'll write the real forces in red. 12.5. So whatever I'm writing in red ink is the real forces. In this it is 0. This is 10. So let me write this outside. 10. BC is again 10. What about DC? DC we got it as compression minus 12.5. Uh, E, this is 72.5. Tension. So let's see, cost equilibrium, whatever we got. 12.5 tension, 10, 10. This is 50. This is compression 12.5, and this is 22.5. So yeah, this is in compression 50. So that is minus 50. Yeah, this is what. Oh, sorry, this is not compression. This is tension 12.5. So these are the real forces. What about the virtual forces? What about the internal forces due to the unit displacement D? Right, which color? So in this, again similarly, we'll have the same thing. This is minus 0.833. This is tensile 0.667, and this is again 0.667. And what about this DC? DC is again tensile. This is tensile. It is complete 0.833. What about PE? PE is 0 in this case also. What about EC? EC we have tension 0.5. Okay. So whatever which I have written in blue are due to the internal forces due to unit load. Right? So I'll just 1 kilo. So now what do we need to find? We need to find what are the numbers we have. Let us say I'll just write it as number. Then what do we have? So we have L, internal force due to the unit load 1 kN, the virtual load of 1 kN, and then the internal forces due to the external load. So number, length, U and P. We have P, U, L. So what are the numbers? So let us write down the numbers first. AB, BC, CE, BD, DE and CE. Then C is already written, so this is DC. CE. We have something DE, CE, CE, BC, and BD. BD, AB, and AD. So again, what is the length of AB is 4, BC is 4, CE is 3, BD is 3, D DE is this. DE is 4, CD 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 is, if this is 3, 4, and this is 5. 5. AD, what is AD? AD is 5. Now U, let us write down what is U. U is internal force due to unit load. So U in AB it is 0.667. In BC is 0.667. In CE, so CE is zero point 0.5. In BD, what's BD? BD. Okay, in BD there is no force. So in BD is 0. What about DE? DE is 0 again. CD, CD is compression minus 0.833. What about AD? AD is minus 0.833. Now what about the internal forces in the truss due to the external load due to the real loads? So in AB it is 10 positive, BC it is 10 positive, which is tensile. CE it is 22.5 positive, yeah, and BD it is 15 positive, DE it is 0, CD it is compressive 12.5, AD it is compressive 12.5. So you can I know that these are zeros. Yes. So this you can simply calculate what are this value, this value, this value, and this value. So total summation. So summation of delta PUL. This will be 191.235. Okay. So what is delta? 1 times delta is summation of U into DL. That is nothing but summation of U PL divided by AE. So we have delta as 191.235 divided by AE. I think we have mentioned the values of A and E. Okay, it's not mentioned. So A is a constant. So yeah, this is the answer. So delta is 191.235 by AE. So any doubts in this so far? These things I didn't calculate because this is just a normal multiplication. So you need to just multiply all these things and then you can find it out. And then you need to sum everything. So you'll get delta UPL. You should also keep something in this mind that in this AE is constant, right? So in some questions, maybe in some questions which you are solving, they will also mention area of cross section of AD as something. For example, in compression, if the members are in compression, the area is so and so. If the members are in tension, the area is so and so. So in that you can't take AE. So in that case, you need to also consider A when you're doing this calculation. So in that you will also have A coming into the picture. So for each member, you will have A1, A2, A3, and so on. In that case, what you need to do is delta PUL by A. You do this. When you get this answer, you just divide it by Young's modulus. If Young's modulus is for all the members, if they are constant, if it is constant. All right. Any doubts in this? Shall I go to the next question? Divided. That's what you can see here. You divide it by A for each term, and then you make the summation. summation of pu l by a, and when you get this answer, then divide it by e. Yeah. So almost all these questions are almost similar. So that is why I'm just giving out solutions for this. I think it is simple, and you can easily manage to find the internal forces. Fine. Let us go to the next one. So we have the next question. Let us take this question. Now, in this question, so we are required to find vertical displacement at joint E. At joint E. So everything is given. Area of cross section is again 400 mm square. We have Young's modulus E is equal to 200 GPa. What about the others? Yeah. The lengths are already given. It's from the geometry we need to take the length. Take the lengths. Okay. So again we have real analysis. Maybe you can start solving, and you can keep giving me the answers. Okay. If you so with that I can skip those steps. So you have this. This is the number. You have one more number here. This is one thing, and this is another one. So you have support A, C, this is A and C, B, D, E, and F. So this is 1.5 and 1.5 and 2. Again, this is similar to this. Similar to this. 1.5. How much is this? Similar to this. You can see here. This is 4. This is 3. This is 5. So everything is divided by 2. It's kind of a similar triangle. So this means this is 2.5. Okay, this is 2.5. Otherwise, you can find out theta, and then you can find out what is cos theta. Cos theta is 4 by 5. Theta is equal to again 53 degrees or something. It will be around 53 degrees something. Instead, you can simply do with the geometry. So, so I think by now you might have found out what is the support reactions. Okay, you have 100 kilonewton acting here. This is a symmetric. You can say this is symmetrically loaded. It's not the symmetric section. You can't say it as a symmetric because the supports are not symmetric. This is pin support, and this is a roller support. So it is symmetrically loaded. You'll have in the vertical direction, in the plane of symmetry, you'll have the loads distributed equally. So you have this is 50, this is 50, this is 50, and this is 50. You don't have any horizontal external horizontal forces. You don't have, so you will not get any horizontal forces at support A. So all right, let us find out the the reactions here. So you have now let us do that by inspection. So we have this at this joint. We have 50 kilonewtons coming from the bottom in vertical direction. So FCD should be 50 in this direction to nullify that. Only then it will be in equilibrium. What about this force in BC? Can anyone say what is force in BC? I'll wait for some time. Can anyone say what is the force in BC? Zero. Yeah, there is no any horizontal reaction. Yeah, BC will be zero. Uh, Similarly, yeah, let us solve for this then. So joint A, 50 kilonewtons upwards, AF, FAF, this is FAE, and this is FAB. This is kind of yeah, we have one joint, we have only two equations of equilibrium, but we have three supports. Let us go and solve for, yeah, this one. Let us solve for this because this joint we have one known, we have two unknowns, so we have two equilibrium equations and we can find it out. So we have 50 in this direction, FDB. You can also use method of sections, but I find this as more convenient than method of sections. So that's why I'm using this. FDE. So what is FDB? FDB times this is theta, that is cos theta should be equal to 50. So what is cos theta in this case? So this is 1.5 divided by 2.5. Again, that is 4 by, sorry, 3 by 5. FDB times 3 by 5 is 50. So this is 250 by 3. So what is that? Yeah, FDB is 250 by 3 in tension. So it is in tension. Force in F. Sorry, can you please repeat? At joint F. Yeah, yeah, you're right. Yeah, there's no. So yeah, correct, correct, correct. Yes. Yeah, we can analyze that. So let us see that also once. So we have this, we have this. So you got this, and what about this in AD? F AD plus 250 divided by 3 times cos theta minus cos theta. This will be zeros. You can analyze this, but let me solve this and then come back to that. So F3AD, FAD plus 50 by 3. What is cos theta? This is theta. How much is this? Yeah, this is 1.5 divided by this again. This is 3 by 5. Is 0. We cancel. This is 50. So this is, how much is this? I'll write it in balance. Let me write it in balance. I know this. How much is this? This is already found out 250 by 3 in tension, and this is compression. Did I get it? Yeah, this is compression 50. This is compression 50, and I need to find this. And someone found this FDE. What is FDE? FDE plus 250 divided by 3. And that should be 4 by 4. So this is theta. Okay. This is 2. This is 2.5. This is 1.5. That means it is cos theta is 2 by 2.5. That is 4 by 5. So 4 by 5, that is 0. This is 50 times. So 200. This was 200 by 200 by. This is 200 by 3. Yeah. How much is this? Did someone found this? How much is this? Fine. Let us say this is x. X times this is theta. How much is theta? So this is, if this is, yeah, cos theta, x cos theta should be 50, right? So what is this theta? Cos theta is this is 1.5 and this is 2.5. So that is 3 by 5 is 50. So this should be 100. Alright. So what about this? This should be tensile, and how much is that? 250 by 3 times, if this is alpha, then cos alpha is this length divided by the hypotenuse. 2 by 2.5, that is 4. So this is 50, this is 200. 200. So if this is 200 by 3, if this is 200 by 3, uh, and this is 250 by 3, so 250 by 3 in this direction, it is again 200 by 3. So this nullifies. That's why the force in this is 0. What about the vertical force BE in BE? So we have this 100 downwards, and this is 250 by 3 upwards, and this is found to be. Let us solve that. Let us solve that. Not having. This is the point B. We have 200 by 3 in this direction, 200 by 3 in this direction, and we have something in this direction, and something in this direction, and something in this direction, and this is 100. This is 0, and what is this? This is 250 by 3. This is 250 by 3, and how much is this? This is x. So 250 divided by 3, and let us say this is theta, so that is cos theta plus x should be equal to 100. How much is cos theta? Cos theta is 1.5 divided by 2.5, that is 3 by 5. So 250 by 3 divided by 3 by 5 plus x is equal to 100. So this is 50. X is intention. So this is 50. Fine. So yeah, that's it. So in this you can see this is 50, 250 by 3, 250 by 3, and 200 by 3, and it is 250 by 3 again, and this is 50 in tension. So what is the question? So in the question it was asked to find vertical displacement at joint E. Okay, vertical displacement at joint E. Now real analysis is done. Let me just yeah, real analysis is done. Now I'll go with the virtual method. Now we have the same beam, and I just copy the same. Sorry, same truss. The same truss. So instead of so now the question is, what is the vertical displacement at E joint E? So at joint E, I'll apply 1 kilonewton force. So you get the reaction 0.5, 0.5 here. Uh, I'll solve only one. Again, you will have 0 here, 0 in this. Okay, and I'll solve for one joint, and then the rest of the joints I'll just give the answer. Maybe you can just cross verify when you're trying this question again. So if this is zero point 0.5, you should have compression here, which is zero point 0.5 again. What about the other one? This is compression, and you have okay. Let us solve for one joint here. So let me solve for this joint. So for joint A, I have FAE, which is in this direction, and FAB. FAB is in this direction, rightwards, and I have zero point 0.5 in this direction. FAE, let us take this as theta, that will be 1.5 divided by 5.5 plus 0.5 is 0. This is 3 by 5. So someone is doing. So FAE is minus 0.5 into 5 by 3, that is minus 2.5 by 3. So FA is again found out to be minus 2.5 by 3. Similarly, I have already worked out. I'll just tell you the values of this. So this is minus 2.5 by 3, and this is found out to be 2 by 3. Okay, and what about the others? This is compression. Sorry, this is tension, which is zero point 0.5, and this is again same 2.5 by 3, and this is 0 as because there is no external force in this should be 0. And what about this joint? In this joint you have this thing, and this would be compression 2 by 3. Okay, this is compression 2 by 3. With this vertical load you have all these things. Let us just summarize, let's summarize these plots, this value. Now I hope it is clear, right? I think you can find it out, right? Vidyadharji, I think Suraj and Mayank, I think you can find out those unit loads. Again, the internal forces due to I'll write down the internal forces due to the external loads as in red, minus 83.33. That is nothing but 250 by 3. That's what I'm tension 50. What about this? This is tension 3.33, and this is 0. This is compression minus 50. This is in compression minus 66.67. What about FE? FE is 0, and AF is again 0. So I'll write the other one in blue. The internal forces due to the unit, the unit, the unit load in the direction of the displacement which we are interested to find, right? So what are those? So this is again minus 0.833. What about this? So this is 0.667. So 0.8333. And what about this? This is 0.5. This is 0. Just don't write 0, and this is also 0. And this is again compression 0.667, and this is minus. You can see some similarity actually. In the real load, in the real loading scenario, what was happening? The loads are acting at B, point B, and the loads are 100 kilonewtons. Okay, the loads are 100 kilonewtons, and the loads are acting at B, which is very fine. If the loads are acting at B, you are getting the same loads or not. Once you are, so, yeah. So in the real scenario, actually the loads are acting at this point, 100 kilonewtons. But instead we have taken 1 kiloton here. So even though if that is the case, we are just getting it as all the loads are actually divided. You are actually dividing it by 100, right? So you can see here this is minus 83.33, this is minus 0.833. So you just check what happens if you are applying the load at B and it is 1 kilonewtons. I think you'll get the same results. Okay. So again, you just write a tabular column. You have numbers, you have length, internal forces due to the unit load 1 kilonewton, and the internal forces due to the external loads, and P, U, and L. So what are the members? Let us take write down the members: A, B, B, C, C, D, B, E, B, B, E, B, D, A, E, E, F, and A, F. So how many members? Did I miss anything? 5 is. So what is the length of AB? AB is 2 meters. What is the length of BC? 2 meters. What is the length of CD? 1.5. DE2. BE is again 1.5. B BD is 2.5. AE The AE is again 2.5. EF is 2. AF is 1.5. What about U? Let us start writing for U. AB is 0.667. BC is 0. CD, which is CD, is minus zero point 0.5 compression. DE minus 0.667. BE is zero point 0.5. BD is 0.833. AE, what is AE? Yeah, AE is again minus 0.833. EF is 0. AF is 0. Let us write P. So P is the internal forces due to the real loads. Okay. So whatever we have written in red color, red, right? So AB is 66.67. BC is 0. CD is minus 50. DE is minus 66.67. BE is 50. BD is 83.33. This is 80 minus 83.33. EF is 0 and EF is 0. EF is 0 and EF is 0. So you just multiply this and write down, multiply this. So you find out and then you summate all this PUL, all these things which you have found out. And then what is delta? Delta is summation of PUL by AE. So you will be getting, yeah. I think in this they've already given the values of AE. So let us know what is PUL. If you just multiply these things, right? I'll just, so this is 0, this is 0, and this is 0. So you need to multiply 1, 2, 3, 4, 5, 6. Let us quickly multiply and we'll find out. 2 times 0.667 times 66.67 plus 1.5 times 50 times 0.5 plus 2 times 0.667 plus 1.5 times 0.5 times 50 plus 2.5 times 0.833 times 83.33 plus 2.5. Yeah, it is. Yeah, I'm getting around 600. Okay, 600 divided by. Let us again write it down. 600 to the power 3. This is newtons. I'm changing newtons. I mean kilonewtons to newtons, and the length meters to millimeters divided by AE. AE is, I think they are given it as 400 mm square, 200 gigapascals. So 10 power 3. 10 to the power 3. So here marks off. We have 8, which is this 600 divided by 7.5. So the answer is 7.5. Okay. Any doubts in this question? You have any doubts so far? In whatever we have discussed. On this, like what's our final result is that at this point E, we have a displacement of 7.5 mm. Fine. So if you want to find out what is the displacement at this point, right? This is again 7.5. This will find it as 7.5. Uh, Instead of finding the vertical displacement at E, if you are asked to find what is the horizontal displacement at D, then the only thing you need to do is instead of applying the vertical displacement at vertical unit load at E, you apply a vertical virtual load of 1 kN at D and find out all the internal forces and you tabulate everything and then you find out the summation of PUL and then divide it by AE. So that happens to the same thing. If someone asked you if in the question it was asked to find out what is the horizontal displacement of this roller support. So this roller support can move in this direction, right? So in this direction can move like if this is what if this is asked, then you apply horizontal virtual load of 1 kilonewton and you solve for the internal forces and then the delta you you multiply PUL and you do the summation and divide it by AE and find out the answer. Alright, so there is one more question. I don't want to solve the entire question. I'll just give you the question. I'll just give you the question and then I'll just take some maybe if you have some notes you can ask me and then so this is again the similar question maybe it requires uh, a little more calculations maybe or a little more this is kind of a lengthy problem, that's what I mean. It is almost similar to whatever we have done today, but this is a little lengthy when compared to other questions. So in this what was asked is find the vertical displacement of joint B. This is what last is, okay. Find the vertical displacement of joint B. So again, what is the procedure? So we have external loads of 4 kilonewtons at each span, at the joints at each span, acting on the truss, and you find out, you solve for, you analyze the truss for the external loads, you find out the internal forces developed due to the external force, and then you find out uh, the deformations due to the external loads. Okay, that is the first part. The second part is wanted to find the vertical displacement at joint what is this joint B. So at this joint, so what is the next part is that you will apply a virtual load of 1 kilonewton, and then you will find out the internal forces due to the vertical virtual load of 1 kilonewton, and then you will tabulate all the forces, but internal forces due to the virtual load and internal forces due to the real loads. You have the length and the area of cross section and the Young's modulus is given as constant. Young's modulus 200 GPa, that means all these sections are steel sections. Then you will you need to multiply, you need to do the summation of PUL and then you divide it by AE. So this is the process. So quickly I'll just solve for one hinge and I'll give you the solution. Maybe you can note down this question and then you can solve for yourself and you can just cross check whether you are getting the correct answers or not. Okay. So in this you can see the loads actually, the loads which are given, right? So these are symmetric, right? The loads are almost it is symmetric in the vertical plane in this particular this axis. So that means you have the support reactions as this is 12, right? So you have 6 kilonewtons here and 6 kilonewtons. Okay. So once you know this, you can go to each hinge and you can start working also. In this hinge, you can directly say this is 4 and this is 4 kilonewtons because there is no other force or other components in vertical direction other than the external force itself. So I will solve for uh, and also okay, what we'll do is we'll just solve for joint E and joint A. Okay, let us see whether we have some symmetry coming in the truss out. Okay. So you have joint E, F, E, F, and this is F, E, D, and this is 6 kilonewtons already acting. So let us say this is theta. F, E, F cos theta plus 6 is equal to 0. What is cos theta? This is 0. So this is 3, this is 4, this is 5. So cos theta is F, E, F cos theta 5 3 by 5 plus 6 is 0. So this is 2 F E F is minus 30. Sorry, minus 10. This is minus 10 kilonewtons. So that means this is the compression. Okay. Similarly, you can say this is again, this is the similar case, right? So you have compression 10, and once this is in compression, you know this, and this is in compression. So what is this is in this direction, so you'll have compression in this coming. So this is 10 times, let us say this is alpha, cos alpha is equal to FHG. So 10 times cos alpha is, this is 4 by 5, this is 8. So this is in compression 8. Similarly, you can find for the others. So you can if that is 8, if this is 8, we have symmetric loading, so this should be 8 in the same direction. This is 8. Okay. So uh, let us take this joint B, joint B. We have, okay, this we didn't find it yet. So this will be 8. Okay, and in this B we have BCF, BC acting in this direction. We have 8 acting in this direction. We have F A B H acting in this direction. We have F P G acting in this direction. What happens with this? So what we do, what we can do is, this is here, this is good. So yeah, we can say these two. Achha, three are unknowns, right? In this, okay, fine. Let us work this point. H. We have H here. One is this way, and one is acting in this direction. This is 10. F H B, and this is 8. So F H B plus 10 times. Okay, this is 10 in this direction. 10 times. This is that is 4 by 5 again. 4 by 5 is equal to 0. So this is 8. So you have FHB as 8. FHB times theta. Is it right? So no, this is theta, right? Sorry. So this is theta. So this is 3 and this is 5. FHB times 3 by 5 is 10. So this is F. Sorry, I made a mistake. You can see here 10 times cos theta is FHB. 10 times cos theta is 3 by 5 is FHB. So FHB is 6 kilometers. Fine. So I'll just write down all the values of the internal forces. You can just verify once you solve the question. So let me write down. So just yeah. So the internal forces are something like this. This is 10. This is 8. All are in kilonewtons. This is 6. Hg is 8. Bg is 10 by 3. Bc is 10. Cg is 4. Gd is 10 by 3. Gf is 8. What about the other one? Yeah, D, sorry, CD is 10. DE is 8. And EF is 10. So these are P's, PIs. So PIs are all these forces which I have already mentioned here. So I'll also now let us go with the unit virtual load, right? Virtual load. So how much is the virtual load, and where should I apply? So I want to find the vertical displacement of the point B. So I'll apply 1 kilonewton here, and then my forces are, so if this is 1, then you'll have this, and you'll have this. So this should be, that is just proportionately distributed. Right? This should be 3 by 4, and this should be 1 by 4. So you'll have AH as 5 by 4, and AB as 1 kilonewton, BC as 2 by 3, CD as 2 by 3, DE as 1 by 3, FE FE as 5 by 12 compression. Okay, then, yeah, this is compression. GF as compression 1 by 3, HG as 1, BG as 5 by 12, and GD as 5 by 12. What about CG? CG will have 0 because there is no force in vertical direction, so this is 0. What about BH? BH is 2 by 3. Okay, so what we can do is, we have U's, we have P, we have U's and we have P's. I'll just copy this. So these are U's, okay, and these are P's. Yeah. So yeah. So these are internal forces. Internal forces due to external loads, or the real loads. And these are internal forces due to unit load. And it is again, you need to tabulate. You have so how many, like the different numbers. You tabulate for the length L, members length L, UI. These are nothing but UIs, and these are PIs. UI, PI, and you just find out UI, PI, LI, and summation of PI, UI, and LI divided by AE. So you'll get this as an answer to around, I think the answer should be around 3 mm, 3.0 something. A and is already given, that's why the answer would be around 3 mm, something like that. Okay, so you can just note down. Maybe you can verify also if you want to give it a try. You can just verify the answers obtained from this. The answer should be around 3 3 mm.